Hi, everyone. It's my honor to present our work here. The topic of this presentation is transformer-based feature learning for image classification. My name is Weichao Li, and I'm one of the authors of this paper. This work is done at University of Electronic Science and Technology of China. My presentation consists of four main parts. Firstly, the background related to the research content and the motivation of the idea. And then the proposed model and the two main modules of the paper will be explained, followed by a discussion of the experimental data and the results. And finally is the conclusion. Firstly, the purpose of few-shot learning is to learn from limited supervised information to achieve the needs of the solution task, which means we need the model can learn a classifier with strong generalization ability under few-shot conditions, as shown in the figure. The training set is first divided into multiple segments. Each segment includes a support set and a query set, where the number of categories in the support set is 5, and the number of each class in the support set is 1, where the number of each class in the training query set is generally chosen to be 3 times than the support set. During the training process, one or more segments are sampled at a time to train the current model. After the training is completed, we can use the training model to input the support set and the query set from the test set to classify the samples in the query set. And this stage is called meta test. So far, there are 3 main approaches to solve the few-shot classification problem. The first is meta-learning. Meta-learning mainly includes model-based and hyperparameter-based method. The second is data augmentation. The basic methods of data expansion include distort the labeled images, image rotation, zooming in and out, etc. The third one is metric learning. Well, metric learning has emerged from the early development of few-shot learning with many classical models, including prototype networks, matching network, CMC network, and relational network. So, why do we choose metric learning? Intuitively, the objective for the classification task is to optimize the feature space in which samples of the same class should be close by the learned manifold, while samples of a different class should be far away. However, in few-shot setting, the research has showed that optimizing feature distance may not necessarily lead to performance gains. Therefore, inspired by the work of finding task-relevant features by category traversal, we attempt to improve the classification performance by considering the context information between different support sets within the whole task. Furthermore, we try to investigate more powerful techniques to exploit the relation between support sets than that used in that work. And the metric learning is far simpler and more efficient than recent meta-learning. The model proposed in this paper has two main contributions. The first point is that the prototype features exaggerated by the prototype network are embedded into transformer by taking advantage of the powerful feature representation capability of transformer, which not only keeps the computational complexity at a low level, but also improves the classification performance by using the contextual information among the support sets. In the second point, the limitations of the traditional cross-entropy loss are overcome by regulating the loss function to cope with the overfitting risk that may be increased by the introduction of transformer. And the labeled assignment of the classification is further improved. Finally, a higher classification accuracy than the existing state-of-the-art methods is achieved. So, it's an overview of our model, called the TML. It mainly consists of three pre-simple modules: prototypical network, transformer, and label refinement. Firstly, images in both support set and query set are input into the prototypical network, and the prototype feature embeddings of corresponding sets are obtained. Then the transformer and label refinement modules are designed for computing the distance loss and the classification loss, respectively. The total loss is a combination of the distance loss and classification loss calculated. Let me specify the prototype network. C1, C2, and C3 are the main centers of the three categories called prototype. And after embedding the test sample X, the distance is calculated with these three centers to obtain the category of sample X. And this network has many advantages. It's very convenient to extend the support set, since there is only one prototype per class. there is no class imbalance. Because there is one feature embedding for one support, we can keep the computational complexity in low level. Transformer is a network based on self-attention mechanism, which consists of encoder and decoder modules. And in this paper, we mainly use the self-attention layer in encoder and decoder. In the self-attention layer, the input vectors are first converted into three different vectors: query vector, key vector, and position vector right here. And the weight matrix is obtained by matrix multiplication and normalization. It is worth noticing that while the convolutional kernel is a local operator, the self-attention mechanism is to extract the further features after the convolution. So the final feature vector containing global features is obtained. Also, we try to improve the classification information used to calculate the cross-entropy so that the classification loss contains components that reflect the distance between samples. And we introduce here the label refinement module to construct a new label matrix refinement matrix by refining the label assignment using the similarity between the query and the support set. We used the dataset mini-ImageNet, which is a subset of the dataset ImageNet. A standard dataset in the field of small sample learning image classification. This dataset consists of 100 categories. Each consists of 600 color images. The whole training process was repeated 200 epochs with 1,000 images each time, and 600 images were randomly selected for testing. The classification tasks are 5-way one-shot and 5-way five-shot respectively. It can be seen that TML, which means our model, provides best performance among all methods for both one-shot and five-shot cases. Especially, TML performs much better than protonites with 10.57% and 5.17% gains in accuracy for one-shot and five-shot, respectively. This can be attributed to the fact that TML built its model on the basis of protonites, and the superior performance is achieved by introducing transformer as well as label refinement modules. In addition, we observe that the superiority of TML is more noticeable for one-shot than a five-shot, indicating TML is more robust for difficult tasks. It is worth noticing that, like TML, state-of-art MetOptNet and CTM are methods that consider the context information of support sets within the entire task. TML still yields results that are superior to MetaOptNet and CTM for both one-shot and five-shot cases. This indicates that the transformer can exploit the correlation between support sets so as to learn highly discriminative features in bindings. This work has presented a few-shot learning method based on transformer which exploits the relation between support sets effectively and efficiently. In addition, in order to cope with the overfitting problem introduced by the increase of model complexity, a classification loss is introduced into the total loss function as a regularization term. Experiments demonstrate the superiority of the proposed method over existing state-of-the-art few-shot learning methods. Okay, that's all. Thank you for your attention.